In this video, we're going to take a look at examples numbers 2 and 3. In the previous video, what we saw is that it's possible to use these parametric equations to create the graph of a curve which is not a function. But one of the additionally nice applications of these parametric equations is that they can be used to model the movement of a particle that traverses, say, the path of some curve out in space. Specifically here in this semester, we're going to be talking about maybe particles traversing some space in the xy plane. So this variable of t that I have can often be thought of as a value of time. Now what I'll see here is that if I was to go ahead and kind of just recopy the picture that I had from before, I could make some adjustments to what I previously had. Let's suppose I wanted to draw the path that this particle traverses along this curve, but only from the values of t being -2 to +2. Well, notice if we look back, this means that I won't need to include this last value up here, where I'm going to have t being the value of 3. So if I was to make this adjustment, I could see that I'm really going to have to get rid of this portion of the curve and kind of just imagine stopping the curve right here. In addition to that, I'm going to kind of have to get rid of this portion of the curve. And I can see that at this first dot, this is when t was equal to -2. This is when t was equal to -1. This dot is when t was equal to 0, t is equal to 1, and t was equal to 2. And so what I kind of see here is that there's a trend or a path that this particle would traverse and an order in which it traverses this curve. And so oftentimes we'll note this direction in which we move by including like little arrows on the curve like I'm doing here. And those show the motion of the particle itself. So this is a pretty powerful thing to be able to do. Another important thing that we might be able to do is to consider how certain sorts of curves can be sketched using parametric curves that are completely unable to be sketched using any other sort of technique that we may have seen before. So as an example of this, take a look at something like the graph of x equals sine y, where y ranges from -2 pi to +2 pi. Now, what I might see about this immediately is that it might appear possible for me to go ahead and think about just quickly rewriting this as a inverse sine of x equals a y. And a lot of times people are very tempted to jump here. But it's important to remember that the inverse trig functions always have restricted ranges. You might recall that the restricted range of the inverse sine function is -pi/2 to +pi/2. That means that the values of y that this function can spit out are limited to only exist within this range. So while I can actually type this into the calculator and hit the graph button, I'll never see values from -2 pi to +2 pi. So how can I do this? Well, again, the idea of parametric equations is what can help us be able to graph this curve. So what we're going to go ahead and do here is to quickly see how we might be able to turn this into something parametric. Well, the first hint that I might be able to notice here is that in every single parametric equation, or in parametric curves or parametric equations, I am always going to have my value of t being kind of bounded between values, like we did in the last example where t was wedged between -2 and +2. So in this case, I'm going to go ahead and say, how about we let y be equal to t? Because if that's the case, then we would know that t is going to have to be between -2 pi and +2 pi, and also we'll get that x is equal to the sine of t. So we have parametric equations that could be written as follows. It's not any different than what we had up above. I'm just going to go ahead and kind of restructure it. So again, these two curves, or functions that I have here, these parametric equations, can be used to create the picture that I want, and I'll just have t get wedged between in these two values. Now I'm going to show you really quickly here how we can actually go ahead and attempt to graph this on the calculator to see exactly how we can understand what this curve looks like pictorially. If I was to switch to my calculator over here, I'll notice that whenever I hit the y equals button, I have curves in there that need to get sketched, and they have y equal formulas. And I'm not interested in those. I want to have a formula that allows me to plug in x's and y's. So in order to do this, I'm going to click on the mode button. And on the mode button, this is where you would normally change from like radians to degrees. But what we're going to do is to go down right below radians and degrees where the calculator says function. And we want to switch it over to parametric option. Notice now when I hit back on the y equals button, I get x1 and y1. And so if I was to go ahead and actually type in the formulas that I had, which was sine of t, and to get a t, I'll just hit my classic variable button where I normally get an x. Now it's ready to give me a t. And I also had y existing as a t. I'll notice that if I click on my window button, I can adjust a couple different things. I have a new T-min and T-max. Well, my T-minimum was negative 2 pi, and my T-maximum, I can actually see is kind of already set at the value of 2 pi. If I was to go ahead then and actually hit the graph button, in this case, I'm going to have to reset my window really quick, but if I reset my window, I can see that I get something that looks like this. Oops. Sorry, when I reset, it actually changed this. Let me try that one more time. Okay, so if I have this, and I have my visuals on the xy plane going from negative 10 to positive 10 in both directions, then when I hit graph, I actually get the picture of kind of like a sine function, but just moving up that y-axis as opposed to horizontally. It's like the inverse sine, only I can see more of it. So this is, again, one of the things that parametric equations are actually good for.